You may start now.
Hello, everyone. My name is Mike Macias, and thank you for attending my MSGIST capstone project presentation titled Modeling Post-Fire Soil Erosion and Sediment Deposition on the Tonto National Monument using the Unistream Power Erosion and Deposition Model. In this presentation, I'll sometimes refer to it by its acronym, the USPED model, just for the sake of brevity. So the objective of my project was ultimately to map soil erosion and sediment deposition, at least the potential for it. But developing the modeling process behind it was just as much of an objective as actually creating the map. I'll begin by talking about the motivating event in the study area to give you an idea of where and why this project occurred. I'll then move on to methodology to describe how I was able to perform the analysis. From there, I'll go on to describe the results and show you what I was able to create. From there, I will then briefly talk about some conclusions and then wrap it up with a questioning. One of these icons is located at the bottom right corner of every slide to let you know where I am or where we are in the presentation. So context is important, so I'll begin with some background information. So in December 2019, there was a very large fire in central Arizona on the Tonto National Forest, about 40 miles east of the Phoenix metropolitan area. This fire was known as the Woodbury Fire, and it burned around 124,000 acres. Here in this map, you see the footprint of the fire. It started just south of the Superstition Wilderness area, and over the course of a month, worked its way northwards towards an area known as Tonto Basin. In Tonto Basin is Theodore Roosevelt Lake and the Tonto National Monument, shown here in orange, which was the study area for my project. Now, the monument itself is an archaeologically rich site. It's best known for its 700-year-old cliff dwellings. On the left, you see the lower cliff dwelling, and on the right, you see the upper cliff dwelling. It was established as a monument in 1907 by President Roosevelt and has been managed by the National Park Service. The monument is relatively small. It only occupies around 1,100 acres at the bottom of a small, steeply sloped watershed. In this reference map, you see the upper cliff dwelling is just south of the lower cliff dwelling. You also find national park infrastructure such as a visitor center, amphitheater, picnic area, administration buildings, and housing for employees. You also see an important ecological area, which is a riparian area. So basically, as Woodbury Fire progressed northwards, it was inevitable it was going to hit the Tonto National Monument. So decision makers there needed to do something in order to protect the archaeological sites and the infrastructure. So as you see here, they decided to do a backburn. It succeeded in its aims. You can see the visitor center was protected, but you also see a lot of area was burned. Actually, over 80% of the monument was burned. Here in this diagram, you see what it looked like immediately before the fire. This is all in the same location, just at different points in time. In this first image, you see a lot of invasive grasses, such as red brome. The second image shows what it looked like immediately afterwards, and the third image shows what it looked like 3 months later. Notice that a lot of bare surface. So after the backburn, decision makers at the monument implemented what's called a BAR plan. It's a burned area emergency rehabilitation plan, which entails erosion mitigation and monitoring. For example, conducting hydroseeding along trails and roads and laying down erosion control blankets. They even use pretty advanced techniques with drones taking imagery and also terrestrial laser scanning with LiDAR to scan the slopes to see how they might change over time due to erosion. So this led to the natural question, can we use GIS to know where erosion is occurring and even to what degree it's occurring? Now, this is an event-based analysis, but by developing a modeling process and a map, this could be used for future fires, future fire events, fire plans in the event there's another fire. So we should all be on the same page when it comes to understanding water erosion. It's basically a three-step process of detachment, transport, and deposition. Essentially, raindrops fall to the soil surface and part of the kinetic energy and dislodging soil particles. As runoff begins to accumulate on the soil surface and runoff is generated, these particles become suspended in sediment and are transported downslope, where they eventually settle on the landscape and become deposited. For a given flow rate, there's a maximum amount of sediment that can be carried, which is known as sediment transport capacity. There's also different types of water erosion. In this project, I looked at rill erosion. You can think of a rill as a small channel of concentrated flow. So before I can talk about the USPED model, I need to talk about another model which is based, which is called the Universal Soil Loss Equation, and its derivative, the Revised Universal Soil Loss Equation. Essentially, they estimate the average soil loss rate based on 6 empirically determined factors. These are the R factor, which is the rainfall erosivity factor, K, the soil erodibility factor, C is the vegetation cover factor, L is the slope length factor, S, the steepness factor, slope steepness factor, and P is the soil conservation practice factor. So the Unistream Power Erosion and Deposition model is essentially the universal soil loss equation, except that the LNS factors are substituted by another parameter seen here in this box, which accounts for slope angle and upslope contributing area U. M and N are constants whose values depend on the type of erosion you're modeling. When you substitute this parameter into the equation, it now becomes a measure of sediment transport capacity flow. But it's not actually, so it's Net erosion and net deposition is determined by what is called a divergence in sediment transport capacity flow. This necessarily entails vector calculus, but essentially, if you calculate the partial derivative components of the sediment transport capacity flow, you can estimate net erosion and deposition. Essentially, in GIS, you can use a raster calculator in these two equations with a slope raster and a slope aspect raster in the steepest slope direction to calculate this. When you add them together, you get the erosion deposition model. Negative values signify erosion and positive values signify deposition. This is what the overall project looked like. This is the overview of the steps. Essentially, it occurred in two main steps. The first step was data acquisition and pre-processing and factor estimation. The second step was actually calculating sediment transport capacity flow and the divergence in sediment transport capacity flow. So to estimate the R factor, I used local rain gauge data. I used this to calculate a 30-year average monthly rainfall and a 30-year average annual rainfall. I then use these parameters in what is called the modified Fournier index. Now, depending on this estimated value, if it fell above or below a 50 millimeter threshold, I would use one of two regression equations. It was below, so I ended up using this regression equation and then calculating an R factor of 68.9. To estimate K factor, while this factor has to be empirically derived by a soil scientist, fortunately, there was a soil study on the Tonto National Monument, which identified 10 soil families, and more importantly for me, to identify the K factor values. Unfortunately for me, this information existed only in hard copy form. This is actually the map that was in the document. It was nothing more than an aerial photograph in which somebody drew on it with a Sharpie marker designating the soil units. Nevertheless, I scanned and georeferenced this and converted to a vector model showing the soil units, and then I converted to a raster model based on R factor values found in the document. To estimate the C factor value, I used National Agriculture Imagery Program data. For two reasons. One, it was high resolution, and two, it had the proper spectral resolution I needed for analysis. And fortunately for me, this was collected, the data was collected just 2 weeks after the backburn event. Here, you clearly make out all dark areas as the burned areas. So I took the red band and the near infrared band raster and calculated the NDVI, the normalized difference vegetation index, according to this top left equation. This gives me a sense of vegetation cover. Here, you can clearly make out the riparian area. I used the NDVI raster inside our second equation, which was a scaling factor to estimate the C factor. I also had to resample this using the nearest neighbor interpolation algorithm to get the estimated raster. Next, I had to calculate the topographic Alice factor according to the equation I previously described. I also used a slope raster. I used an M and N value of 1.6 and 1.3 because I wanted to look at real erosion. This necessarily entailed using a 1 meter digital elevation model by the USGS. I used a DA flow direction model to calculate flow accumulation, and I was able to obtain this raster. There's also the P factor raster. Even though there was erosion control efforts, for example, placing erosion control blankets or even constructing small rock check dams, there was no spatial data for this, nor did I consider it significant enough to include in the model, so I did not. Now that I had each factor in raster format, I input them as the USPEN model, and in the raster calculator, I calculated the sediment transport capacity flow. I needed two additional rasters, the slope raster and the slope aspect raster, which show the compass direction of the downslope. Again, to calculate divergence and sediment transport capacity. So this is what the model looks like in ArcGIS Pro's model builder. The important point is that so far I've discussed the first half of the model. Now it's just a matter of calculating the second half of the model. To do this, I broke the sediment transport capacity into its X and Y components. I then computed the components change in sediment transport capacity in the X and Y direction. Using the slope tool and the aspect tool to obtain 4 derivative rasters. These were then input into the partial derivative equations and added together to get the net erosion deposition. I know I've said a lot, but here's the final product. So this is the net erosion deposition map of the Tonto National Monument. It's classified to show areas of high erosion, moderate erosion, low erosion, stable areas, low deposition, moderate deposition, and high deposition. I also determined the amount or the percentage of the monument, or at least the raster that covered the monument, based on erosion type and deposition type. So it's probably better to look at something like slope or even elevation range. I used the zone statistics table tool to calculate the majority statistic to give me an idea of what was the most common type of erosion or deposition per zone. So if 11 degrees or less, they were predominantly stable. Slopes from 7 degrees to 12 degrees were predominantly low erosion, and slopes from 13 degrees to 9 degrees were predominantly moderate erosion. In terms of elevation range, the top quarter of the elevation range predominantly showed low erosion, while the bottom 3 quarters of the elevation range predominantly showed moderate erosion. If you look at this map at a larger scale, and you look at it at least qualitatively, you can see the less or the The flatter ridge lines showed low erosion, whereas mid-slope showed moderate erosion, and the bottom of the slope showed high deposition, which is what you might intuitively expect. You could also clearly make out the stream channels, which show high erosion, and given the high volume and high velocity of flow through these areas, they clearly show up. You could also notice some areas within the stream channel having high deposition. And if you've ever seen a stream channel after a fire, there's a lot of deposition and erosion occurring in these channels. I also looked at them as a three-dimensional local scene in ArcGIS Pro, just to give a more realistic view. Whether it's a two-dimensional map or a three-dimensional scene, this, for the layperson, could easily make out which areas are at least more important, per se, when it comes to erosion mitigation and monitoring. So overall, my project succeeded in creating a post-fire soil erosion deposition map of Tonto National Monument, and it was successful in developing a methodology and identifying data to do this, which again could help with future bar plans. Like any model, there's room for improvements. There's no doubt errors. There's no doubt that there are errors in this model. It's a very simple model. For example, errors when digitizing the soil units, and assumptions were made for sure. I made assumptions about the rainfall data, but ultimately I think it comes down to field verification and field observations to verify the results of this. It's been 3 years since the backburn event, so it wasn't really conducive or possible to go out to the field and assess things, since vegetation regrowth is pretty much what it was before the fire. But I can see trying to look at this model in more recent fire and actively going out to the field to see if the results even line up at all closely. So that pretty much sums up my project. I just want to thank the National Park Service, specifically Jade Robinson of the Tonto National Monument, and my advisor, Dr. Fernando Sanchez. Without their help and understanding and patience with me during this past couple months, I would not have been able to complete this project. Thank you for your time, and I'll take any of your questions.